So these are the items we'll go through, and I think many of these things could be some revision for you because these are like basic concepts. The word statistics, as you know, has two different meanings. When we talk about statistics as a plural, we are talking about the data that we have. And that's why whenever we use the word data, whether you are writing a report or if you are writing a research article, we always say data are. We don't say data is, because data are treated as a plural. Data, as you know, is a representation of a reality. So there is some reality somewhere, and we cannot capture everything, or we cannot capture that reality exactly. So we make use of data. So data just represents a reality, but there is a difference, like both are not equal. Data is not equal to reality. So data is only representing reality in whatever way. So sometimes it may be able to represent it up to a very close level, but in many cases it may be able to represent only with a big gap. So there could be a big gap between the reality and what data tells you. But as a plural, statistics stands for data. But as a singular word, it means science that you can also say like data science, but science that deals with collection, analysis, interpretation, and presentation of data. Statistics is not only applied at the analysis stage, but a lot of efforts are put in, a lot of ideas of sampling are used even at the time of data collection. So in fact, there are situations where we collect data in a very structured way, and there are situations where we are not able to collect data in a very structured way. You have seen difference between what is called observational data, where we just observe and collect that information, as compared to data that are collected based on some kind of experiment where there is a very specific structure. So for example, an auto company, they want to improve something in their engine that gives a high mileage, and they want to carry out experiment by changing some parameters in the engine, basically design, and then collect the data before and after. So that's a very structured kind of thing where you are making some change and observing what happens. But at many places, even data is collected just based on the observation. What you see, you collect. Now, data collection obviously is a very important area because the quality of data will dictate whether that data is going to be useful later on or not. If the data is not good, if data is faulty, as they say, GIGO, GIGO, garbage in and garbage out. So no amount of sophisticated and very complex statistical analysis is going to salvage a poorly collected data. So statistical methods cannot help in any way if the data is not collected properly. But if data is collected with good quality and we apply appropriate analysis method, then we also need to do proper interpretation of the data. There are times when people have some like tendency to interpret data in their own way, like what they want to interpret, but one has to be very, very careful that the interpretation is done correctly. Even if somebody does a very good job of data collection, analysis, interpretation, but there may be times where that has to be presented, and if the presentation is not effective, if data are not presented properly, analysis is not presented properly, so people may start suspecting something is wrong. So presentation nowadays also plays a very, very important role when we talk about data and statistics. So this is a comment by H.G. Wells almost 100 years back, but it's very relevant even today. Statistical thinking will one day be as necessary for effective or efficient citizenship as the ability to read and write. So I think in anywhere you apply, whatever job you want to do, you'll find that statistics and statistical methods, even thinking, plays a very important role. Now, what is statistical thinking? So it is a philosophy of learning and action based on following three fundamental principles. The first principle says all work occurs in a system of interconnected processes. Now, what is a process? So, process could be anything. It could be attending a lecture is a process. Education is a process, like somebody enrolls in a program and goes through a process. Working on some project, so that also is a process. In manufacturing, an item has to go through like different processes, and somewhere there is a bending operation, there is a cutting operation, there may be milling operation, there may be assembly. So there may be like many different processes. Not only in manufacturing, even non-manufacturing or services, you have all kinds of processes. So accounting could be a process, marketing, the way somebody makes a GDP forecast, so that could be a process. So the first principle says that all work, everything occurs in a system of interconnected processes. The basic definition of process is that a process takes an input, and then there is some value addition, and then there is an output. So every process has some input, and then some value addition takes place, hopefully, and then there is an output which goes to a customer or a consumer or the next person. Second principle is variation exists in all processes. There is no process on earth which has no variation. In fact, another way of saying this is that there are no two things which are alike in this world. Variation always exists. Let me take one example from manufacturing. So there is this manufacturing process where some kind of cutting operation takes place, and there has to be a certain dimension that product needs. Maybe like the width should be 3 centimeters, and obviously it's very difficult to produce a lot of items with exact dimensions. So they also give some tolerance, like it could be plus minus, so plus minus 0.05, something like that. Let's say in that process, at the end of the day, they have produced about 10,000 of those items. Now, if somebody picks up two items out of that 10,000, is there a chance that those two items are exactly same? Because we are saying variation always exists and two things cannot be alike, but is there even a small chance, even like very tiny probability, that if I pick up two items and measure their dimension, they may be equal? Or you feel there is no such chance, it cannot happen, because this principle says that variation exists in all processes. Anyone like to answer that?
Sorry, your audio cut out for me, so I didn't get the question.
Okay, so let me repeat my question. I see there are 39 people. So let's say there is a manufacturing process which has made 10,000 items at the end of the day, which need to be of certain dimension, like 3 centimeters in width. So I'm just trying to see whether this principle is really valid in real life or not, because this principle says variation exists in all processes. But if I pick up two items, is there a possibility, even a like small possibility, that both of these items are exactly same, maybe 3.1 centimeter, exactly 3.1? Or it cannot happen. Out of 10,000 items, if I pick up two items, I cannot get two items of exactly same dimension. So do you think it is possible or not possible? Anyone?
I think it's possible, but the variation is over a large sample size. Definitely there will be an amount of variance across the all the items.
No, forget about large sample size. I'm only saying two items. Is there a possibility out of 10,000 items I can find two items which have exactly same dimension?
Yes.
Yes.
There could be some possibility, right?
Yeah. Mhm.
So first item is 3.1 centimeters and second item is 3.1 centimeter. So there is a small chance that out of 10,000 I can find two items which are 3.1 centimeters. But if I bring a slightly more powerful measuring instrument that can measure up to second decimal, so it may happen that it is 3.16, but second item also could be 3.16. If I bring even more powerful measuring instrument that can measure up to three decimals, maybe this is like this and this is also like this, exactly same, exactly same, exactly same. Now if I ask you, is it going to continue forever?
Not.
So we can imagine that if we continue to bring more powerful measuring instrument, this is not going to continue forever. At some place you may find a difference.
Mismatch. Yeah.
So that's why the second principle, when it says no two things can be alike, remember in the beginning I mentioned data is only something that represents reality. It's not reality. But what is the real dimension of an item and the second item? So we can only approximate it subject to many things like measuring instrument and the importance, like how far you want to go and things like that. But at some level the variability is bound to happen. Even like a mother who has like twins, and to an outside person twins look exactly same, but obviously mother is able to figure out that this is A and this is B because she knows them more closely. Basically her least count in terms of like measuring instrument is more powerful than somebody who is looking at those kids from outside. You can imagine like looking down from a 10-floor building from a balcony and you see like a lot of people. So everybody may look same in terms of height, but as you start coming down of that tall building, at some point you'll start seeing that somebody is taller, somebody is shorter, and so on. So second principle basically says variation exists in all processes. That means we cannot get rid of variation. Variation is bound to be there. Understanding and reducing variation are key to success. Variation cannot be zero. You cannot like rule out variation in a process, but if you can understand that variability, where it is coming from, what are the sources of variation, and try to reduce that variation, you are going to improve the process. So success basically means improvement. In words of Deming, he says for businesses, variation is enemy number one. Any process that you have more variation, that is your bigger enemy. You have to fight and try to reduce that variation. Sometimes people may confuse something else for variation where it is not really variation. So one example I will give you is when you are looking for food, will you go to a restaurant that gives you just one type of food or a lot of variation in terms of your what you can choose?
Variation.
So a lot of people will like to see more options. But one thing you should remember is that's not the variability we are talking about. So this variability is not that variability. This variability is, if I go for a coffee at Starbucks and I order a coffee, on one day it has same coffee, it has one taste, and second day it is totally like different. Same coffee tastes different, and first day it was very hot, second day it was just warm. We are talking about that variation. So that variation is the enemy, and reducing that variability always helps. So as a customer, you will be happy if there is a consistency, there's not too much of variability. If you buy a car, for example, and the company says that this car will give you 50 miles per gallon, and then your friend has a car, exactly same car, and he or she gets like 65, so you feel bad that my car is only giving 50. So initially you may be happy, but now your friend has a better mileage, so you may not be happy that I have the same car and how come I'm getting such a low mileage. So we are talking about that type of variability. So understanding and reducing variation are always key to success. So whenever we do any analysis, we try to keep this in mind at the background, like what is the context, what variability we are trying to understand, and how it can help. Statistical thinking can help in understanding the process, understanding the variation, even like what kind of data should be collected, how it should be collected. But then there is a second branch, which is like statistical methods, which may be a combination of study of variation, your data, statistical methods or tools. So it is important to realize that where the data is coming from, where the variation is coming from, what is the context, what is the process. So that's what statistical thinking tries to highlight. Statistics or statistical methods or statistical tools can be very broadly divided into two categories. One is descriptive statistics, where we try to understand the data through tables, or you make graphs and charts, or you may do numerical summary. So most of the EDA work, exploratory data analysis, is part of descriptive statistics. And the second major area where usually people spend more time in terms of your learning is statistical inference. So what is statistical inference? So statistical inference is basically a journey from sample to population. So in statistics, you usually come across two terms. One is called population and the other one is called sample. And because of various reasons like time, cost, and other things, it's not practical, and most of the time it is not possible to get data on each and every element in the population. So what we do is basically, statistics is all about working smartly. So we try to work smartly by taking a sample. So we save on time, we save on cost, and many other things. But when we take a sample out of population, we are taking that sample to understand the population, maybe some aspect of population, it could be mean, variability, or anything else. So that's what we are trying to understand through sample. But on sample, we do all kinds of analysis, but ultimately our aim is to go back to the population. So whatever our conclusions are, whatever our inferences are based on a statistical analysis, we are trying to go back to the population. So actually the journey is from population to sample, and then sample again to the population. Because it's not really the sample in which we are interested. We are more interested in the population, and sample is just the means. But when we take the sample, obviously we have to take into account many things. We have to be very careful. We have to make sure that that sample is a representative sample. When we take a sample from the population, we hope or even we try that it is something which represents the population. I know, like, we just finished elections and next elections are very far away, but if you have to predict who will be the next president, and if you take a sample of 1000 people but all living in Boston, so obviously that's not going to be representative sample. So sample has to be representative of the population, and then only, like, whatever magic statistical method can bring, we can do that. When we do descriptive statistics, we make visual summaries. Histogram is a very common example. So if you think of data related to aging in accounts receivable, and somebody took a sample of 600 observations, so if you make a histogram, we look for three things. One is the general location where the values are concentrated. Usually those are captured by mean or median or mode, depending on the context. Mean is very good measure of location if data is symmetric, but if data is skewed, usually people go with median. But histogram can give you some idea where the general location is. And then the second thing we are interested in a histogram is spread. How much variability exists in the data. You can see this is like slightly over 60 days to about 115 days. So that's the range of these accounts receivables. So that much time it is taking. And the third one is shape. So this you can see looks like a symmetric pattern, inverted bell-shaped kind of pattern. So this is with 600 observations. If I have 5000 and if the data is symmetric, it can start representing in many cases a normal distribution curve that you see here. We have talked about normal distribution earlier also, that it's a very important idea in statistics, and it is the basis for many of the statistical techniques and tests. It has two parameters. It can be completely described with two numbers or two parameters. One is mean, the other is standard deviation. The tails on the left and the right can extend to infinity, means it could be very large. Having a very large or a very small number also has some small probability. Theoretically, these tails never actually meet x-axis. It keeps getting closer and closer but never meets. It's like if you are standing in front of a wall and you can move only 50% of the distance every time, so you'll never be able to reach that wall if you are moving only 50% every time. So it never meets, but the area under the total curve is 100%, or in terms of probability it is 1. And because it is symmetric, if you cut it into half, left of the mean you have 50% area, and right of the mean you have 50% area. So the mean and standard deviation can change the shape of the normal distribution. So in this picture, for example, if mean is same and if you change the variability or standard deviation, you may get a different pattern in terms of tallness or flatness. So for example, distribution number 1 that you see here, the blue one. So do you think it has the highest variability of the three or lowest? Obviously lowest. The brown one has the highest variability. You can see the tails are extending well beyond first and second normal distributions. I'll call this week 4. So I just want to show we can very easily make a normal distribution in R. So statistics and R are good friends. I'm going to create so let's collect some x-axis value of a normal distribution using sequence between 10 and 30 with increments of 0.1. So 10, 10.1, 10.2 up to 30. And then a simple plot of this x, and then DNORM. We'll use this x values, and because we are using numbers between 10 and 30, so I was assuming that we have mean of 20 and we'll use a small standard deviation of 3. So it gives you a normal curve something like this, but these are all dots which we can convert into a curve using type. So you'll see under type you could use many things. P for point, L for line, so let's use L. So it looks like a normal distribution curve. So this is a standard normal distribution with mean 0 and standard deviation 1. So that's the property of standard normal distribution. Theoretically, between plus minus 1 standard deviation, if you go one step on left, one step on right, and if your step is equal to 1 standard deviation for standard normal curve, so you are covering about 68.26% of the area under the curve. Out of 100%, 68% is just within plus minus 1 standard deviation. If you go further away, if you take 2 steps on the right and 2 steps on the left, so that area is about 95.4%. And plus minus 3 sigma distance, which has a total length of 6 sigma, is about almost everything, 99.73. So only 0.27% is beyond the plus minus 3 standard deviation limit. So that's a well-known property of normal distribution. But the thing is, we never get this very beautiful normal distribution curve in real life. Like when you collect data, when you make a histogram, it will not look like a perfect normal distribution curve. So empirically, like based on the data, typically this plus minus 1 standard deviation, it will range between 60 and 75. And 90 to 98% within plus minus 2 sigma. And because your sample usually could be small, your 99 to 100% of the data may be within plus minus 3 limits. So 95% of the population is within approximately plus minus 2 standard deviation. These are also called z-scores. This x-axis is actually a z-axis. So g is a transformed variable where mean is 0 and standard deviation is 1. Z basically stands for standard normal distribution where mean is 0 and sigma is 1. So that's what Z represents. So z-score to probability, you'll find that usually we do 2 different types of calculations. One calculation is for finding the probability or finding area under the curve. So how do we do that? So first one, for example, says what is the probability. So this is how I will read this equation. So P stands for probability. So what is the probability that z-score is less than 0.94? So z less than 0.94. So what we do is we look at a normal distribution with mean 0 and sigma 1, and we locate this value which is 0.94 just below 1, and we want this area to the left, all this area to the left. So that's what we are interested in when we frame this P z less than 94. So we want to find that, and you can find that in R just by using this formula. So P stands for probability and NORM for normal distribution. So if you simply put 0.94, it will tell you that the area is 0.8264. So this is the area to the left of 0.94. So that is one type of calculation. Given the value of z, we are trying to find the area. And then we also do a reverse calculation or inverse calculation, where we start with the probability and then find a z value. Something like this. So probability of z less than equal to question mark. So we are interested in finding that, such that it gives you an area of 0.8264. So I'm using the same number just for simplicity. So what value of z will give this area? So if you are finding that inverse calculation, instead of p, we have to use q. So that's the only difference between these two. So use q and norm, and then the area, it will tell you the value is 0.94. So let's look at this question. Assume that average number of days account receivable is on the books until funds are received is 25. So this is the average. So because somewhere it says assume normal distribution. Suppose this is your normal distribution and this is 25. So very difficult to write with the mouse. Standard deviation is 4. So this is the situation. Now the first part says, what are the chances that account receivable is not closed before 30 days? So that's the line. Now my question to you is, should I be interested in area to the left or to the right? If you read these wordings, what are the chances that an account receivable is not closed before 30 days?
To the left.
Right.
Right, because not 30 days.
Yeah.
Not 30 days. So like it takes more than 30 days. So we are interested in this area. We'll go to our friend. So the first question is about area to the right. So because the total area is 1, if we do 1 minus p norm, so that should give us area to the right. And we are interested in the value of 30 or above. So we use 30, average was 25 and sigma was 4, right? So it tells us 0.105, so about 10.6%. What we are doing here is we are finding x greater than 30. How many days does it take until 20% of the account receivables are booked? So now we have the area and we are interested in the value of x. So again, you have a normal distribution. 20% means somewhere here. I'm just drawing a line to the left of the middle because area to the left of mean is 50%. So obviously we have to go further away from mean to get 20%. So this is 0.2. So the question is, what is this value? So now we use the second type of calculation. So Q norm 0.2, 34, not 30, actually 25. Mean is 25. So that value is about 21.6.
Every time that we're doing P norm and Q norm, is it only for are we finding the only left side of the graph? Because when you said 1 minus P norm, it means that we're finding the right side. Would it be the same thing for Q norm? So by default, I just assume it is only on the left side, right?
Yeah, with default, it's left side. And if we need to go to the right, we do 1 minus. So if you recall, when I was talking about statistical inference, and I mentioned that we have something called population, we have something called sample. So any book you read, anywhere you go, whenever like you hear population, with population we always talk in terms of parameters. So populations always have parameters like mu, you see mu, sigma, or whatever. And whenever we talk about sample, we always talk in terms of statistics. So sample statistics like x bar, which is for mean, or small s for standard deviation, or p for proportion, and so on. We never have something called sample parameters or population statistics. So there's no such term where we say population statistics or sample parameters. So it's always population parameters and sample statistics. So that's the convention we use. And sample statistics such as mean, standard deviation, proportion, it could be median, anything, these are only estimates of the population parameters, like corresponding parameters are mu, sigma, or p. They are never same. They only estimate what could be population parameters, which is usually unknown. Since there is a variability in these estimates, like if I take a sample of even size 100 from a population and calculate average, maybe it's a manufacturing process and they are looking for a very critical dimension, which is width of a bar, and you take 100 samples on one day and find the mean. You take 100 samples another day from the same process, find the mean. The means may not be same even for like samples. There's bound to be variability. So because individually the values vary, x bars will also vary. So since there is a variability in these estimates from sample to sample, we can quantify uncertainty using CIs or confidence intervals. We cannot capture the real mu or real population parameters with just one number. If we have a good estimate, still there will be some gap between the reality and the observed value or observed mean. So they may not be exactly same. So the better way could be if we have a range. Confidence interval is nothing but a certain range. So let's say I want to predict the next US president, and I collect the data and I find that candidate A will get 46.5% of the votes. Now the population parameter, we don't know whether it is going to be exactly 46.5 or it may be something else, 49, who knows. But based on our data, we find it's 46.5. But that's a single estimate. It's a single number and it's bound to be wrong. It cannot be exactly same as the population value. But instead of 46.5, we also anticipate, because of sampling errors and all that, that there may be some plus minus 2%, 3% variability. Now 46.5 plus minus 3, so suddenly you have a range, and that has a much better chance of capturing the real value compared to a single value. So confidence intervals basically give you more confidence of capturing the real population parameter. Confidence intervals provide us with a range in which population parameters are likely to fall. Any specific question, anyone? I think Sophia, you are there, right, today?
Yes, I am here.
Did you see any question which is unanswered yet?
No, I don't believe there are any unanswered questions.
Okay. So what is a confidence interval? So usually you will see 90 or 95% or 99%, because these are like round numbers people use. And 95% confidence interval can be interpreted as approximately 95 out of 100 confidence intervals will contain the population parameter. So using sample mean or standard deviation or whatever we are interested in, whatever aspect of population we are interested in, this is what we can do. Let's say there's a 90% confidence interval and there is 95% confidence interval, like the band or that plus minus term that I talked about. Let me draw a picture and call this 1 and call this 2. So I would like to know which one is 2. Is it 90% or 95%? given all background conditions similar, same data, everything same, which one?
95 is true.
5.
So 2
is
is
95.
associated with 90% or 95%?
95.
I also see 95 more, but 90 also. So let me ask those of you who feel it should be 90%. So 90% people, whoever like mentioned 90%, why do you think this is 90%?
Because it's a larger range of values. So in the 90%, you'd have more. Your
So you
interval would be larger.
so you mean like because 95% confidence is a higher confidence, so the values will be more like accurate, and 95% is lower, so the values will be maybe less accurate. That's the feeling, right?
That was my feeling.
I'm sure there may be a few more like that. So let me give one quick example. I know you have got like, you know me only through a small screen that you see on your laptop or computer. But if I ask you to guess or give me a guesstimate, not estimate, but guesstimate of your, like what do you think is my weight in pounds?
170.
Okay, so somebody said 140 also. Okay, but let's go with 170. This is a single number. This is one number. In terms of statistics, we will call a single number as point estimate. So this is a point estimate because this is a point, just one number. And we know that with one number, we can never be right. The two value will never be exactly same as the estimate. If I ask you to give me a range like plus minus, so that you are more or less sure that, or you have some level of confidence that it may be within this. So plus minus, I see values from 140 to this, so let's say plus minus, somebody said 10, so basically it means 160 to 180. Let me ask Shukri.
Yep, yes it is.
Okay, because you said 170 plus minus about 10, so anywhere between 160 to 180 is your confidence interval. But if I put a bet, I put a condition that if this doesn't capture my true weight, you have to pay me $10,000. But before you, like, we decide whether you'll have to pay me 10,000 or not, I will let you change this interval so that you want to be sure you are not losing any money. So instead of 10, what is the number you will tell, like plus minus? So somebody says plus minus 100.
Yep, I would change it to 100.
Yeah, so definitely you cannot be wrong now, like almost 70 pounds to 270 pounds. So you cannot be wrong. So now your confidence level is like almost 100%. You're sure that you are not going to lose money. Earlier you were not sure. So earlier your confidence level was less. Your confidence level was less, but your interval was very narrow. Now your confidence level is like 100%, but your confidence interval is very wide. So now you see what happens when you increase the confidence level from 90 to 95%. What will happen to the interval? It is going to increase to the extent that the interval becomes sometimes meaningless. Like if I tell a political party that I carried out a survey and my survey is almost 100% accurate, but the confidence interval is like 46.5 plus minus 40. So that survey is of no use to that political party. So that whatever money they have spent on me in carrying out the survey is going to go totally waste, because a very wide interval like 0 to 100% is total waste. So the key thing is when you try to increase the confidence level, your interval will go up. Another thing to remember in statistics or in a statistics class is that your confidence level will never be 100%. It's not possible. As long as you have a population and you are taking a sample from population, your confidence level cannot be 100% because sample is imperfect information. It is a subset of the population. It's not population. It tries to represent a population, but it is not true population. So in that sense, you'll always be lacking something. And that's why confidence level, it can be like 99.99999 something, but it will never be 100%. The meaning of confidence interval is a 95% confidence interval suggests if you make approximately 95 out of 100 confidence interval will contain the population value. So if this middle line 100 is the real value, and if you create 100 different confidence interval with the same data by taking repeated samples, it can happen that like sometimes like here 3 4 5 times out of 100 your confidence interval you can see doesn't capture the true mean. True mean is here, the population mean is here, but you can still be wrong 5% of the time. In other words, it means that if we had 100 different samples, created 100 different intervals, 95 out of 100 would contain true mean. We are saying 95. We are saying 95 in the long run. And if you physically start taking like samples 100 times and try to see really whether it is capturing or not, you may not be able to get exactly same answer in 100. It may happen that out of like 100 times, it captures only 94 times, even though you are saying it is a 95% confidence. So there could be a variability even there. But in the long run, like if you take a very large sample, about 95% of them are likely to contain your value. So confidence intervals are often wrongly interpreted. We are confident in the process of finding confidence intervals, not in any one interval. We cannot say that there is a 95% chance that the population mean is within my interval. No. So that's an incorrect interpretation. So we cannot say that 95% confidence means this is my 95% confidence interval and I'm 95% confident that the real value is somewhere here. So that's not the correct interpretation. Confidence level is not the probability that a specific CI contains the population parameter. The parameter is unknown, constant, and no probability statement concerning its value may be made. So somebody gives a warning, we should not do that. So he is the original developer of confidence intervals, so we have to follow what he says.
Wait, sorry, can you just repeat one more time what a confidence interval is? If it's not, so it is not a the probability that the model parameter is the actual population parameter. So can you?
A 95% confidence interval does not mean my confidence interval has 95% chance that the actual population value is within that. So it's not telling you that this confidence interval that we make from the sample has 95% chance, but it is talking about the process. So that's important, which means if I'm in this situation, maybe it's a final inspection in a company and every day they are taking such samples and based on that they are making confidence intervals. So out of 100 days, let's say each day they make one confidence interval. So their decisions will be right 95% of the time, but there's a chance that 5% of the time they may be wrong. So The key thing is a 95% confidence interval suggests that approximately 95 out of 100 confidence intervals will contain the population parameter. So that's the correct interpretation. Not that here is a confidence interval, see, here is a 95% confidence interval, and then I start saying that there's a 95% chance that this interval contains the population value. So that will be incorrect. The confidence level, which is like 95% or 99%, tells us how likely it is that the method that we are using will produce an interval that captures the population parameters if we use it many times. So 95% of the times we are going to capture the population parameter. The confidence level does not tell us the chance that a particular confidence interval captures population parameter. Instead, confidence interval gives us a set of plausible values of the parameter. So we are trying to emphasize the same thing in so many different ways. So typically for confidence interval, we use 1 minus alpha. Alpha we can use to represent something called a risk level. So 1 minus alpha could be 0.95. If you are talking about 95% confidence, 1 minus alpha will be 0.95. So 1 minus alpha is called the probability content or level of confidence or confidence level. Alpha within this is the opposite of confidence. So it is known as significance level. So that's a statistical term. It's also called statistical significance or the probability of being wrong. So risk level, what is the risk? So if my confidence is 95%, that also means my risk is 5%. So 5% of the time I'm likely to be incorrect. Confidence intervals are made under different conditions. Confidence interval for means are very common. One situation where we make confidence interval is where population variance is known. That there could be a situation where a company may be carrying out some activity day in and day out, and they have very good idea of what is the possible variability, and they might use it as a population variance or standard deviation. So basically it means population variance means in this equation of x bar plus minus remaining term, this sigma is known. So this sigma is a population parameter. Usually population parameters are represented by Greek alphabets, and sample statistics we use terms like x bar or s, those kind of things. Now this formula has two parts where x bar is known as point estimate. X bar is nothing but a single value, and that's the point estimate of average. And then there is a term after plus minus, and that whole thing is called margin of error. Like this candidate will win or will get 46.5% votes, but we may say the margin of error is plus minus 3%. It may go up and down. So that plus minus term is called margin of error. How much error we can expect in our estimate. Now within this margin of error, if you recall, sigma divided by square root of n, there is a name for that. Anybody remembers what is this called?
Is it the standard error?
This is our standard error. So standard error basically represents a variability in the distribution of x bars. And because we are trying to find a confidence interval for x bar, so x-axis of that normal distribution is not x but x bar, and variability is captured by standard error sigma divided by square root of n. And then depending on how much confidence you want in your interval, like 95% or 99%, we will use a z value. So z comes from standard normal distribution, and this will take care of whether the interval is for 95% or 99% and things like that. You see, this is a standard normal distribution here, and to find z alpha by 2, so if you recall, 1 minus alpha is the confidence level, and if it is 95%, then alpha is 0.05, and if alpha is 0.05, half of that is 0.025. This is alpha by 2, and this is another alpha by 2, and you can get z alpha by 2 using that Q formula, because given the area we are trying to find out what should be the value of z. And this number is very popular, like 1.96 for 95% confidence interval. Sometimes we don't even calculate. We know that it's 1.96. Let's look at this example here, where you have transaction cost of tellers versus ATM, and this bank collected a sample of 45 transaction costs. That's the sample size n. Average is $1.45. And then there is a very important statement. It is known from previous experience that the population standard deviation is about 0.32 or 32 cents. So now this problem actually has population standard deviation known. So this falls strictly under case 1 where sigma is known. So we can use that formula. And the question is, if the transaction costs are normally distributed, and frankly speaking, we have a sample size of 45, and we are talking about confidence interval of average. So even without that, we may have been able to use normal distribution. But there are a lot of inputs, very specific inputs, like population standard deviation is known, it follows normal distribution, and then find the confidence interval. So it's a straightforward application, and there's a library called BSDA which has this function. Z is for standard normal distribution, SUM for summarized. Because these numbers are summarized, we don't have the actual data. We have the summaries, like average is 1.45, but we don't have actual values for all 45 samples. So we use z-sum, and we say that the mean of x is 1.45, sigma 32 cents, sample size 45, and confidence interval we want is 95. And as soon as you run that, you get your 95% confidence interval. So automatically when you say sigma dot x, it knows that, and also because we are saying z-sum, it knows that we have to use normal distribution, and this is sigma known case. Now if you go to the next question, where you have this company which manufactures a certain type of bar with tensile strength of 93 kgs. Several customers complained about deterioration in average tensile strength of recently purchased bars. So customers are now feeling that the strength is not that much which has been advertised. So as a part of investigation to check validity of these complaints, an engineer has performed destructive testing. So for tensile strength, actually they have to perform destructive testing. They have to break the bar by pulling them, and it's expensive testing, so you cannot go for a very large sample, but they took 23 and they found average to be 92. Although I say here calculate 95% confidence interval, and your population standard deviation is 4.7, and whether the concerns of the customers are valid, so all those questions are there, But if you step back for a second and look at this situation, the company says we will provide you these metallic bars with 93 kg strength. And then your own engineers collect data and they see that these bars are 92. 92 is less than 93. So my question, anybody like to answer, is do we really need any statistical method or confidence interval or test of hypothesis to prove that 92 is less than 93? Or can we conclude that the customer is right? Remember, we always say customer is king. So we say customer is right because we took 23 samples and our average is 92. And customers are complaining that it's less than 93. So do we really need any further proof? Or this is like, I don't know, I think lawyers may say open and shut case. Or mathematicians may say hence the proof, QED. So do you think 92 is like, ask anybody, they will say 92 is less than 93. So do you think customer complaints are valid?
I think it's less than a quarter of a standard deviation difference. So some statistical test is probably a
Maybe.
better.
Okay, so I think I feel you are a very strong person because I tried my best to put a trap and lead you in that direction, but I think nobody fell for it. So that's a good sign. Remember, when we do a test, X bar is only one small component of this whole story. You have Z, you get some knowledge from standard normal distribution, you get some knowledge from sigma, you get some knowledge from sample size, and then these statistical tools, they blend everything, they put everything together, and then they say what is likely happening. So it gives you much more educated direction than ignoring the variability part. Remember, statistics is all about like studying variability. So we cannot jump to any conclusion only by looking at X bar. Margin of error, we have no idea unless we calculate. But if somebody has been working in that field day in and day out, so that person may be able to see very quickly with sigma and all that maybe customers have a problem. So let me put this in. So we are using a function called zsum test. Mean of X was given to us as, or the engineers calculated as 92. Actually, sigma was known because they might have been working with this kind of data for years. So they know that it is about 4.7. Engineers took a sample of size 23 metallic bars. Mu, which is assumed here, is 93. That's our value of interest. So let me do this first. Forget about everything else, and okay, I'll have to run these libraries first. This one gives me a confidence interval from 90.1 to 93.9. Default is 95%. I did not specify anywhere, and you can see 93 very safely falls within 90.1 and 93.9. So statistically, there is no difference. You collect data next time, there is every possibility that your X bar is 93.2. So we do not look at 92 at its face value, but now we are baking into the calculations, the variability sigma, sample size, z, everything, and then it tells us that the range is this. So clearly 93 is included here, and customer concerns are not that valid. You can do test of hypothesis even with confidence intervals, but if you want to do more formal way, you can include your mu that you're comparing. You can also specify confidence level 0.95, and actually out of the null hypothesis and alternate hypothesis, our alternative is if the value is less than the mu 93. So we can also specify that, and you get a p-value of 0.15. So this is very high. So if you want to conclude with 95%, we would say that there is no proof that the value has deviated significantly from 93, or it is statistically significantly below 93, because p-value is not that small. So if it was 0.05 or less, then we could have concluded with 95% confidence that there is a change in strength, but not with this. Now, second situation is when sigma is not known, and this is the most common case. Most often we don't know the population value, so we replace sigma with S. S is the sample standard deviation, and instead of normal distribution, now we have to use t distribution. So that's the only difference. Otherwise, the structure of the formula is same. So you have the point estimate, and then plus minus you have margin of error. And this margin of error is based on the t value and standard error for your data. So t distribution, I mentioned earlier also, it's similar to normal distribution because it looks like bell-shaped curve. The only thing is that it has thicker tails. So area under the tails is larger than what we observe for normal distribution. But as the sample size increases, t distribution becomes closer and closer to normal distribution. So if you recall, z value for 95% confidence interval for normal distribution was 1.96. So you can see with 1000 it reaches exactly 1.96. Even with 100 it comes very close. But when your sample size is only 5, and if you use 1.96, then it can make a big difference. So the higher value is basically going to increase the width of the confidence interval. So it's going to be more realistic.
May I understand this way, like t distribution is for larger sample and the z is for population?
A t distribution is when your sample size is small. Actually, it's the other way. We use t distribution usually when sample size is smaller. And when sample size is large, like 1000, then there's no difference between t and z. Even with 100, t and z is standard normal distribution. So both are very close to each other. But when your sample size is small, you can see t distribution says the value is 2.78, but standard normal distribution, the value is 1.96. So you see there is a big difference.
Yes.
Okay. Here is example of sigma not known, where we use that formula that I showed you. So you have HR manager who is analyzing some data of 57 financial planners, and what he or she finds is average is 52,746 with a standard deviation this. So what is the 95% confidence interval for mean compensation. So very straightforward. When you have n, this is x bar or average, this is s, sample standard deviation, and 95% confidence. So use the formula. So instead of z, we are using t here, and format is similar whatever I showed you earlier. The only thing is, instead of sigma dot x, now you have s dot x because this is sample. So it gives you a 95% confidence interval. Similarly, CNN Money reports that mean cost of speeding ticket, including court fee, was $150 in 2012. And police department claims this amount has increased. So to test this claim, they collect data using a simple random sample of 160 drivers. So 160 is good sample. And find that they paid mean of $154 per ticket with a standard deviation of 17.54. Now the question, like obviously we want to verify, we can do confidence interval, we can do tests of hypothesis. But the key question is whether this is sigma known case or sigma not known case. So I have mentioned sigma not known, but when you read this, it nowhere says that this standard deviation is based on the population. It says that data with 160 drivers was collected and that gave a mean of 154 and a standard deviation of 17.54. So it is very clear that the sample standard deviation is provided and we have no knowledge about the population variability. So clearly this is the second situation and we have to use t-distribution. So that's why you see we use t here. And once you plug in the values, you get a p-value which is quite small now, 0.002. So if you want to conclude with 95%, where alternative is that true mean is more than 150, so we end up rejecting the null hypothesis because p-value is less than 5% or 0.05. So whenever p is small, we tend to reject null hypothesis. Now another situation is where we are working with proportions data, but the format is same. You have this point estimate and you have this margin of error. Proportions, it is using standard normal distribution z, and we can estimate the standard error here using this formula. So if we are using z sum dot test, we can supply the top part, which is our s. S will be square root of p and 1 minus p. Once you have that, you can supply that and do the calculation very easily. Now coming to situations where you have two population. Nowadays PlayStation is very popular, so Sony would like to test hypothesis that average age of a PlayStation user is different from those of Xbox user. So they collected 36. So that's the sample size for PlayStation, and they found average age 34.2. Xbox sample of size 30, average age is 32.7. And population standard deviation for age is given. So this is sigma known case. So p is not significant, means there is no proof that the average age of PlayStation players and Xbox players is very different. Another example, actually here it very specifically says S and not sigma. So this is sigma not known. So now t-test will be fine. So this is about tires, and you have average for both type of tires, and S square, remember S is standard deviation, S square is variance, but the format is same format. X is the first population and Y is the second type of population. You plug in the values and it will give you the outcome very easily. I want to do one more test, and this time not average, but we want to compare variabilities, because sometimes variability is also important. And this is chart for Apple from January 2019 to end of 2020. So how Apple stock has performed, you can see a lot of variation. But if you calculate returns, return is like from one day to another, how much the stock price changes, you may see this kind of pattern. So let me actually take you to R and do this. So make sure you have installed and ran these libraries. So first I have to get data. Now getting stock market data is very easy in R. So one of the libraries has this function called get symbols, and the ticker symbol for Apple is AAPL, and we have to specify the dates obviously from to. So let's say we want 2019 January 1st to 2020. So second number is month, so December 31st, so just 2 years. So it collects some data. If you want to look at the plot, you can do chart series. Our data is in Apple, so it will immediately plot. And you can also put a square bracket if you want and specify any specific year or month. If you want, let's say 2019 December only. So this is how Apple behaved in December. This is a candlestick formation, and this is a very popular way people look at these charts. It looks like a box plot, but it's not exactly a box plot. If you look at this one, the lowest point is the low of the day, highest point is high of the day, and then if it is green, that means it opened here and closed up. But if it is red, it means it opened higher and closed lower. So red means it was down for the day from where it started, and green means it was up. So this is 2019 December, this is 2020, and you can see. But usually when we try to analyze this, we try to get something called returns. I will show you. If I click on Apple, you have opening price, high price, low price, closing price, etc. So let me create return and say within that calculate returns AAPL, and with the dollar sign I want to use apple.close because closing prices are usually the most important ones. So if you look at return, first one will not have a value. The reason is the way we calculate return is second value minus the first value divided by today's value. If I have to do that, I will copy this here in the console. 35 minus 39 divided by today's value 39. Because it was down the next day, it comes to negative 0.099 in terms of returns. So if you look at that value here, that's the exact value that we get. So this is how it calculates returns, but first row is missing value, so I'm going to get rid of that before I do anything. So with square brackets, if I say -1 and run, if you look at return, so that first missing value is eliminated. So now we have data in every cell. If you want to do a histogram of return in, let's say, 2019, so this is the histogram you saw on that page. if you change it to 2020, so notice when we convert the stock prices into return, usually they will hover around 0. And there are days when returns are much better, or there are days when returns are very low. The way we test this is we use VAR for variance.test. And then you can compare return for 19 versus return for 2020 and see whether there was significantly different variability in those 2 years. And actually visually we can see there was a difference, and p-value also indicates there was a difference because p is less, much lower than 5%. Now another example I want to give is, this is also a test of hypothesis where we do test of independence, where we make use of frequency data in the form of a contingency table. So you'll see one example of a contingency table here. Color of eyes and hair of people in Caithness. So this is a place in Scotland. Somebody collected data and they want to see if color of eyes and color of hair of that city, so is there any dependence or it is independent of each other. Null hypothesis is eye color is independent of hair color, and alternate hypothesis is eye color is not independent of hair color. So that means it depends. And the most popular test we do in these situations is chi-square test. And this is the function that we use. You simply use the function and it will give you a p-value. And because p is less than 0.05, this is how we conclude. Since p is less than 0.05, we reject null hypothesis and conclude with 95% confidence that eye color is not independent of hair color. One thing to emphasize is the way we do test of hypothesis and the way we conclude, we always talk in terms of rejecting null hypothesis or failing to reject null hypothesis. You will never see a language where we say we accept alternate hypothesis or we reject alternate hypothesis. We always speak in terms of null hypothesis being either rejected, or if we don't have like enough evidence, if p-value is much higher than 0.05, then we conclude that we cannot reject. But the focus is always on H0, null hypothesis. Either we are rejecting it or due to lack of proof in our data, we are letting it go. So that's the kind of language we use when we conclude based on any test of hypothesis. Another example of testing hypothesis. So we have seen like one population situation where you have a normal distribution or t-distribution and you are doing few things. Then we saw example where you have two populations and you want to compare like PlayStation versus Xbox people and see whether their ages have similar distributions or not in terms of mean. But there are many situations where we are not comparing mean of one population or two population, but even more than two. There may be a situation where we have like 3 different means. So one example is given here. And this is a number of cylinders in a car on x-axis and miles per gallon on y-axis. You have this data from empty cars, and visually you can see actually there is a big gap between the box plots, and sometimes even that should be enough. So when it is visibly very clear that the major part of the boxes are not even overlapping, and then there may be even like the tails, there is hardly any overlap. So that's an indication that even statistical test will prove they are different. but just for the sake of completion, I have done this test. So null hypothesis is the three means are equal. Alternate is not all means are equal. Now somebody may say, why not we do this? Why go for a new method when we already know t distribution? So why not do this? We compare mean at 4 with mean at 6. So first x bar we compare with the second x bar. And then we compare first x bar with the third x bar. So because we have three means, one comparison will not do. We may have to carry out more than one comparison. But the problem is if you are concluding something about the comparison of means, when you compare like first time two means with 95% confidence, second time again you are concluding with 95%, third time again with 95%. So what happens is, if you multiply 0.95 times 0.95 three times, if you are making three comparisons, your confidence level drops to 85%. And sometimes you may have four comparisons or 5 or 6. So that could be a problem. But then there is a method called analysis of variance. We'll talk about this in more detail later on also. But there's a method called analysis of variance, which helps us to compare more than two means in one analysis. And it uses a F value. So F here is for Fisher. As you may know, like Fisher is known as father of modern statistics. So he is the one who has done a lot in this field. And analysis of variance method was created by Fisher. And it says P is obviously very small. So we can certainly conclude, we reject null hypothesis and conclude with 95% confidence that the number of cylinders has statistically significant impact on miles per gallon. The data I used, empty cars, cylinder it thinks is a numeric variable, but it's actually a factor. So I can convert that into a factor very easily with this line. So I had put a cylinder on the x-axis and MPG on the y-axis. I had colored the boxes with like separately for the cylinder, and then I add the layer to specify the geometric shape, which is box plot, and this is what I showed you there. And to do ANOVA or analysis of variance, the function is AOV. So MPG tilde CYL cylinder and data is empty cars. So if I save this, let's say in A, and then you want to look at ANOVA of A, so you'll be able to generate analysis of variance table very easily. A plot that you may find very useful in these conditions is plot means for MPG versus cylinder and the data empty cars. Just a quick type. So this is the plot I showed you there. For each level of cylinder, like 4 cylinders, 6 cylinders, 8 cylinders, it says the first one has a sample size of 11, second one 7, so slightly less, and third one they got data with 14 cars, and then you have 95% confidence intervals, and you can see there is hardly any overlap. So no wonder p value is very, very small and you get it statistically significant. This was the plot that I showed you there. It's one way because we are using only one variable. Miles per gallon is response, but the variable of interest is number of cylinders, CYL. So it's one way. Okay, then if no more questions, I'll see you next week. Have a good weekend.
Thank you.
Good night.